Hello friends, today we shall discuss variational problems in parametric form. Consider the functional consider the functional v xt comma yt equal to the integral from t0 to t1 f txy x dot y dot dt. This equation is denoted by 1, where x equal to phi t and y equal to psi t for t is less than or equal to t1, greater than or equal to t0. In order that the values of the functional depend only on the line and not on the parametrization. It is both necessary and sufficient that the integrand in one in equation 1 does not contain t explicitly. And that it is homogeneous of the first degree in x dot and y dot. Here x dot means dx by dt and y dot means dy by dt. Thus capital F x comma y k x dot k y dot is equal to k capital F x y x dot y dot, where k is greater than 0. This is denoted by 2. For example, vxt yt is equal to the integral from t0 to t1 phi xt yt comma x dot t y dot t dt, where phi satisfies the homogeneity condition 2. Let us now consider a new parametric representation tau is equal to xi t where xi dot t is not equal to 0, x equal to x tau, y equal to y tau. Then the integral from t naught to t1 phi xt yt x dot t y dot t dt is equal to the integral from tau 0 to tau phi x tau y tau comma x tau dot tau xi dot t y dot y tau dot tau into xi dot t t tau by tau dot but since phi is a homogeneous function of first degree a homogeneous function of first degree in x dot and y dot so phi x y x tau dot psi dot y tau dot psi dot is equal to psi dot phi x y x tau dot y dot tau. Hence the integral from t0 to t1 phi x y x t dot comma y t dot dt is equal to the integral tau 0 to tau 1 here tau 1 phi x y x dot tau y x tau dot y tau dot dz d tau. Thus the integrand remains unchanged. With a change in the parametric representation with a change in the parametric representation now the arc length the integral from t1 to t2 x dot plus y dot power 1 by 2 dt and an area bounded by a certain curve one by 2 the integral from t1 to t2 x y dot minus y x dot dt are the examples of such functionals. Here we see that this is point A, point B, T naught, T1. This curve is x equal to xt, y equal to yt, t is less than or equal to t1, greater than or equal to t naught. Since we know that ds is equal to ds square plus dy square, this is equal to dx square plus dy square. ds is equal to under root dx square plus dy square, under root dx by dt whole square plus dy by dt whole square dt. Arc length AB is equal to T naught to T1 x dot square plus y dot square dt. Here phi x y x dot y dot is equal to under root x dot square plus y dot square. Now phi x y k x dot k y dot is equal to under root k square x dot square plus k square y dot square. This is equal to k under root x dot square plus y dot square. This implies phi x y k x dot k y dot is equal to k phi x y x dot comma y dot. So here we see that the under root x dot square plus y dot square is homogeneous function of degree 1 in x dot and y dot. Similarly, x y dot minus y dot x is also homogeneous function of degree 1 in x dot and y dot. In order to find the extremals, of the functionals of this kind vxt yt is equal to the integral from t1 to t2 phi xy x dot y dot dt, where phi is a homogeneous function of the first degree in x dot and y dot, and also for functionals with an arbitrary function phi t x y x dot y dot. We have to solve a system of Euler's equation. We have to solve a system of homogeneous equations phi x minus t by dt of phi x dot equal to 0 and phi y minus d by dt of phi y dot equal to 0. This is denoted by 3. To find the extremals, we must consider one of the Euler's equation 3. And integrate it together with the equation defining the choice of parameter. For example, to the equation phi x minus d by dt of phi x dot equal to 0, we can adjoin the equation x dot square plus y dot square equal to 1, which indicates that the arc length of the curve is taken as parameter. Now the Weierstrass form of Euler's equation 3 is the Weierstrass form of Euler's equation 3 is 1 by rho is equal to phi x y dot minus phi x dot y upon phi 1 x dot square plus y dot square power 3 by 2, where rho is the radius of curvature of the extremal and phi 1 is the extremal and phi 1 is the common value of the ratios phi 1 is equal to phi x dot by y dot square is equal to phi y dot by x dot square is equal to minus phi x dot y dot by x dot into y dot. Thank you for your attention.